So last time I showed to you the indeterminate forms. And indeterminate forms, they arise when we evaluate, or sometimes they arise when we evaluate the limit of functions. And when you evaluate the limit of functions, and the form of what you see is any one of the following forms, then what you have there is an indeterminate form. And so when you say the form of your limit is indeterminate, that means you cannot yet determine the limit of the function. You cannot yet tell the limit. You cannot yet be certain about the limit. And so you must not rush into making a conclusion about the limit of your function. So in this video, I will show you a few or in fact 2 ways. There are many ways, but for now, I will show you 2 ways to find the limit of functions that show the indeterminate form. So from the previous video, we saw that this is an indeterminate form because this one is a rational function, and we can directly apply your theorem on rational function f of a over g of a, or in this case, it's f of 3 over g of 3. And what we have here is 0 over 0. So this one is an indeterminate form. And so you cannot yet make a conclusion that the limit is 0 or the limit is 1. Okay, so do not rush into saying 0 divided by 0 is 1. That is not true. Okay, so this is what we do. By now, you should be kind of familiar with functions that appear like this. I hope that you can recognize that this one has a common factor because x squared minus 9 is just equal to x minus 3 times x plus 3. This one is divided by x minus 3. And so it has a common factor. X minus 3 divided by x minus 3 is 1. And so you are left with x plus 3. So this one is equivalent to x plus 3. We can now evaluate the limit of x plus 3 as x approaches 3. And what is this? This is equal to 6. Find the limit of 2 divided by x minus 1 times x squared as x approaches negative infinity. So we discover this to be of the form, so 2 times or 2 divided by x minus 1 as x approaches negative infinity, that is equal to 0. And the limit of x squared as x approaches negative infinity is just infinity. So this one is an indeterminate form. Okay, so what do we do? What I will do is I will multiply these 2 functions to produce a rational function. And if we were to apply our limit theorems on this, this one, it turns out, is also an indeterminate form. 2 times negative infinity squared, that is just infinity. And this one, negative infinity minus 1, is negative infinity. So this is still an indeterminate form. But this is what we can do with 2x squared divided by x minus 1. This one, 2x squared divided by x minus 1, it's equal to this. 2x squared divided by x minus 1 times this factor. This one is just equal to 1. So multiplying it to this one will not change your function. And look at this. So 2 times x squared divided by 1 over x, that is just 2 times x. And you will distribute 1 over x to x, and that becomes 1. So look at that. X times 1 over x is 1. And 1 times 1 over x is 1 over x. Okay? And so let us now evaluate the limit of this function as x approaches negative infinity. So 2 times x as x approaches negative infinity is just negative infinity. Now look at this. So what is the limit of 1 as x approaches negative infinity? 1 is a constant, so that's just equal to 1. What is the limit of 1 over x as x approaches negative infinity? That is 0. So negative infinity divided by 1 is just negative infinity. So the limit of our function, the limit of this function as x approaches negative infinity is equal to this, negative infinity. You know what? I was kind of rusty. When I was preparing the slides for this topic because I haven't taught limits in a very long time. And so I just want to verify if what I got here is correct. And so what I did is I sketched the graph of the function 2 times x squared over x minus 1. Okay? I sketched the graph of this function, of course, with the help of GeoGebra, and this is what I got. So what is the limit of this function? What is the limit of our f of x as x approaches negative infinity? And this is the graph. So let us investigate. So this is the horizontal axis as x approaches negative infinity. Our function approaches negative infinity. So we got it correct. It's negative infinity. So before I go to the next slide, I just want you to pay attention to how we wrote our solution. You know what? When teachers see a solution which is so disorganized, most likely your teacher will just cross it out. So this is the direction of your writing when you are writing a solution. You begin from left to right and top to bottom. That is how you write a solution. And then when you have no longer enough space here, what you do is you go to the next column. And again, left to right and top to bottom. This one is an indeterminate form, and it took the form of 0 over 0. So what do? You produce a factoring for both the numerator and denominator and look for common factors and cancel them. So that's one way to solve the limit of an indeterminate form. In the second example, we saw something like this. This is 0 times infinity, and when we wrote it as one rational function, we found something like infinity over infinity. Still, this is an indeterminate form. So what did we do? We multiply the rational function by an expression something like this. 1 over x to the n divided by 1 over x to the n, where n is the least degree between the degrees of the numerator and the denominator. You know, your numerator and denominator, if they are polynomials, they have a degree. There are many ways to work out the limit of functions that give rise to indeterminate forms. And we will talk about them as we go along with the topic of finding the limits.